Recall that if I wanted to encode a sequence of all zeros using bipolar AMI, I would do that with a flat voltage level of 0. However, in this video, unlike in the previous one, I'm not using paper that has lines on it. So by looking at this signal, I don't know how many zeros I'm encoding. That depends on the rate at which the zeros are encoded. This could easily be 5 zeros, 10, or 20. It depends on how frequently I encode a signal element. Now, when a sender and a receiver are communicating, they know what data rate they're communicating at. So the sender explicitly breaks up the signal into elements of the same length or duration in time. So each segment of this signal corresponds to exactly 1 0. However, the sender and the receiver are at two different locations, and they can only communicate via these signals they're transmitting. And they each have their own internal clocks. So although the sender is transmitting the signal regularly at discrete intervals, the receiver may receive the signals at different intervals, because over time clocks can tend to drift slightly out of sync with each other. So let's assume that the receiver and the sender start with their clocks synchronized. So the receiver would also interpret this as the start of the first signal element. But as this signal covers long distances, as time passes, the clock of the receiver gets a little bit out of sync, and so we have a very small error here. So the receiver thinks that this is the end of that signal element. So far, there's no problem. But if this sort of error keeps happening repeatedly, then we'll keep drifting farther and farther away from where the boundary should be, to the point that we've now lost one of the zeros that was sent. The number of elements that the receiver will count in this interval is one less than what the sender actually sent. So the clocks are getting out of sync, and that is causing data to be lost. And this sort of clock drift can go in the opposite direction as well, causing the receiver to interpret the signal as having more zeros than was actually sent. So a way to avoid this is needed. Now, note that with bipolar AMI, we don't have a problem if we send lots of ones for the following reason. Let's say that I want to send a signal of all ones. This is what the sender would send if it wanted to transmit all ones. Now, it is still possible for the receiver's clock to drift, but if the receiver thinks that this is the point at which this interval should end, it will be corrected in that false assumption by the fact that the voltage suddenly drops at this point. So the receiver will actually reset its clock to have this as the end of one interval and the beginning of the next. So each time the signal goes up or down, the receiver actually resets its clock to stay in sync. This means that as long as the receiver sees a change in voltage level frequently enough, it will be able to reset its clock and avoid getting out of sync. Now, we can't guarantee that any given signal will periodically have some number of ones in it, but we can use a technique called scrambling to assure that even if the sender sends a long sequence of zeros, we will encode that signal with some changes in voltage level that the receiver can use for synchronization. To see how this works, we will encode the following bit sequence. If we want to encode this bit sequence using bipolar AMI, then we will have a problem. The problem is that we have these very long sequences of zero voltage during which the sender and receiver's clocks could get out of sync with each other. So we need a way of providing synchronization information to the receiver in this interval, and potentially also this one. There are two scrambling schemes we will discuss. The first is bipolar with 8 zeros substitution, or simply B8ZS. Now, this encoding scheme is based off of bipolar AMI, but will encode sequences of 8 zeros in a special way. Specifically, we'll use the following table. This table provides a sequence of 8 different voltage levels that can be used to replace a sequence of 8 consecutive zeros based on what the preceding voltage level was. So in this signal here, we start off with a 1 which is encoded with a positive voltage, and then a 1 which is encoded with a negative voltage. Then we have a sequence of 8 zeros. Now the sender knows that it's going to be sending this sequence, so it checks in advance and will replace these 8 zeros with one of these two patterns. Specifically, because this one has a negative voltage, we will go to this table and look at the negative row and use this sequence of voltage levels to replace this sequence of 8 zeros. The result looks like this. So at this point, I've encoded the 8 zeros here. After that point, we have 2 more zeros, and because 2 is not 8, we simply encode those in the normal fashion, and the rest of this signal is also encoded in the normal fashion. So a sequence of 4 zeros doesn't bother B8ZS. It takes 8 zeros in a row to cause a substitution. Now, the obvious question is, how does the receiver distinguish these fluctuations that are actually encoding zeros from ones? Well, if we remember the rules of bipolar AMI, we'll see that each subsequent one is supposed to have the opposite voltage level of the preceding one. But in the binary 8-0 substitution scheme, we have a 1 encoded with a negative voltage here, and then some zeros, and then a negative voltage again. Having a negative voltage follow another negative voltage like this is actually a violation of the encoding rules for bipolar AMI. Then after this violation, we have a positive voltage, a 0, a positive, then a negative again. These two positive voltages in a row are also a violation of the regular bipolar AMI encoding scheme. So what we've done is we've constructed a voltage sequence that breaks the rules. However, we're going to make a special exception for this voltage sequence. Normally, if you see a voltage sequence breaking the rules, it means that some sort of noise has distorted your signal so much that you can't read it properly. But this particular pattern will be recognized by the receiver and interpreted as all zeros. So, once again, we won't mistake these for ones because this is a code violation. But unlike other code violations, it's one that we expect. Now, the reason that we have this table is that if the 1 that came before my sequence of 8 zeros had had a positive voltage rather than a negative one, then starting with a negative voltage here would not have been a code violation. That's why in the case of a positive preceding voltage, we use this flipped sequence of voltage levels. Because we have replaced this sequence of 8 zeros with this substitution sequence, we shouldn't have any problems with clock drift, because once we have our third 0 in a row, we start having changing voltage levels, which allow the receiver to reset its clock. So as long as we are certain that the clock will not drift so much as to be out of sync within a period of 3 zeros, this scheme should work fine. This scrambling technique is commonly used throughout North America, but there is another common scrambling technique that is more common in Europe and Japan. It is known as high-density bipolar 3 zeros. So this scheme will actually replace every sequence of 4 zeros with a different specially encoded sequence. It has a slightly more complicated substitution scheme that depends on this table. Every time a sequence of 4 zeros is encountered, the sender must determine what the sign of the preceding pulse was and how many ones that had occurred since the last substitution event, specifically whether or not that number is odd or even. So let's use this scheme, which is also based on bipolar AMI, to scramble this signal. The ones are encoded the same as usual. First a high voltage, then a low voltage. Then we have our first sequence of 4 zeros. Now, because the preceding voltage is negative, that puts us in this row. Then we count the number of ones that have occurred since the last substitution. Now, here we only see 2 ones encoded, but to make this result interesting, let's say that a third one was encoded previously, so I actually have an odd number of ones that have been encoded by the time I reach this point. That means that these 4 zeros get replaced with this substitution. So I will have 0, 0, 0, and then a negative voltage. Once again, I have a violation of the normal encoding rules for bipolar AMI. I have a negative followed by a negative. That means the receiver will notice the error, but because the error is in line with expectations, it will interpret this 0, 0, 0 minus sequence as being 4 zeros. However, immediately after this we have 4 more zeros, and we have to decide how to encode that. Well, we just had a substitution. So between the last substitution and this one, there have been 0 ones, and 0 is an even number, so now we are in this column. However, the sign of the preceding pulse right here was still negative. So we'll be using this substitution, and we'll be putting a plus 0, 0 plus to represent 4 zeros in sequence. Now, the jump from this negative to this positive voltage could be seen as a 1, but then once this code violation is seen, this positive following this previous positive, the receiver will realize that actually these 4 elements should all be zeros. Next we have 2 zeros, and we simply encode 2 zeros the way we normally would. But now it is time to encode another 1. Now, because the preceding voltage here was positive, this 1 will be encoded with a negative voltage. And note that although this does obey the rules for bipolar AMI, we go from a positive to a negative, it actually results in a different voltage level for this one than what we received for both bipolar AMI and binary 8 with 0 substitution. The reason is that the way in which we substituted the zeros with other voltages necessitated that the next one we encode have a negative rather than a positive voltage. After this 1, we have 4 more zeros. So at this point, we have had a single 1 since the last substitution. Therefore, the number of ones that have occurred is odd, and the sign of the last pulse was negative. So we actually have this exact same substitution occurring again, which consists of 3 zeros and then a negative pulse. And so this is a violation, so these 4 signal elements will be interpreted as zeros. And then at the end we have another 1, and because we just had a negative pulse, this 1 is encoded with a positive pulse, which once again differs from what was used in bipolar AMI and binary 8 with 0 substitution. So we have yet another scrambling scheme, and we're doing more substitutions with this scheme because we substitute sequences of 4 zeros rather than 8, and the one you use really depends on the environment that you're in and how frequent you expect clocks to become out of sync with each other. But the general principle is the same. If you're sending a long sequence of flat voltage, you need to artificially insert some voltage changes so that the receiver will be able to synchronize its clock with the sender.